Today we're going to look at the graphs of the reciprocal functions, cosecant and secant. Remember, the whole idea of a cosecant is that it is the reciprocal of the sine. Cosecant of any angle is the reciprocal of the sine of that angle. So, since we already know the sines of all of our special angles, finding the reciprocals shouldn't be that hard. We'll start with kind of the table of values for the sine of x, and then take its reciprocals. I've got the graph of sine of x there kind of in the background to help you remember, but hopefully you know these special angles anyway. The sine of pi over 6 is 1/2, which means its reciprocal is 2. Pi over 6, by the way, remember it is about a third, it is exactly a third of the way to pi over 2. So pi over 6 is right there. You notice how its sine is 1/2, and its cosine is 2. Sine of pi over 4, we know this one also. We know it is root 2 over 2, but remember that comes from rationalizing the way it showed up originally was 1 over root 2. And it's helpful to think of it that way because when we take the reciprocal of it, it's a lot easier to just have plain old root 2. Which, by the way, hopefully you remember this, is about 1.414. So at pi over 4, the cosecant has shrunk to about 1.4, right about there. The sine of pi over 2, well, we know that one is 90. The sine of 90 degrees is 1, and so the reciprocal of 1 is also 1. So at that point, the sine and cosecant are going to be at the same place. And then as the sine, remember in the second quadrant, the sine starts going down from 1. So its reciprocal is going to start going up from 1. By the time it gets to 5 pi over 6, all the way over there, its sine is back down to 1/2, which means its cosecant will be back up to 2. And throughout the path in the middle, it'll be kind of symmetric, following this path symmetrically. The question is, what happens next? What happens as we get bigger and bigger to pi, or closer and closer to pi? Well, remember, the sine of pi is 0. Right? That's that intersection right there. But the reciprocal of 0 doesn't exist. There is no such thing as a reciprocal of 0. And we saw this with rational functions also. When a denominator gets closer and closer to 0, you get closer and closer to a vertical asymptote. And that's going to happen on the other side too. I didn't graph it here, but remember what would have happened if I would have included the line above it for 0. The sine of 0 is 0, and so the cosecant of 0 must be undefined as well because you can't take the reciprocal of 0. So we would have had a vertical asymptote there also. And so that's the graph of cosecant through the first 2 quadrants, between 0 and pi. In the next 2 quadrants, remember the sign repeats itself. It's just everything's negative instead of positive. The sine of 7 pi over 6 is negative 1/2. So the cosecant of 7 pi over 6 would be negative 2. The sine of 3 pi over 2 is negative 1. So its reciprocal is also negative 1. And just like the sine of pi is 0, so the cosecant of pi doesn't exist, the sine of 2 pi is 0, and so the cosecant of 2 pi also doesn't exist. So there's going to be a vertical asymptote there too. But everything is on the negative side. And so the pattern does repeat itself over and over and over again every 2 pi radians. There'll be a positive swing for the first pi radians, and then a negative swing for the second pi. And so we can write our domain. This is going to look a lot like with our tangent. The domain, again, we can't describe what x can be because of all those undefined points. So instead, we'll just define what x cannot be. X is not equal to any multiple of pi. X can't be 0 or pi or 2 pi or 3 pi. the period, be careful about this. It's tempting to say, oh, if x, the domain is restriction is happening every pi radians, it's tempting to say that the period is pi. But remember, the period has to include the positive swing and the negative swing. So the period is that full 2 pi that it takes to go through the whole cycle. And then after that, it'll just start repeating itself. And down here, it would have repeated itself down here also. We can name the asymptotes. Remember, the asymptotes in the domain, it's the 2 sides of the same coin. The domain, we're listing everything that x can't be. So we'll use the not equal to symbol. For the asymptotes, we list all those times when x has a vertical asymptote, which are the same things as the domain restrictions, just with an equal sign instead. And you may have noticed I've been pushing off the range. The range is a little bit more complicated. It's certainly more complicated to write. I actually need a little bit more space, so I'm going to write it down here. The range, it seems like, oh, we've got arrows pointing up, arrows pointing down. It should be all real numbers. But no, because there's all of this space in here where the graph never touches. So all of this space is not in our range. The range can only be everything else. So when we list the range, what we're going to say is that I like to do it in interval notation. If you prefer inequality, you can. But I like to say that the range is everything from negative infinity to negative 1. It's describing everything down here, including 1, of course, or everything from 1 until infinity. And that's the range. It's a little bit weirder than the domain, but it's not too bad. You can also, of course, say this as an inequality. Y is less than or equal to negative 1, or y is greater than or equal to 1. Either way of saying it is great. And our graph for secant is going to be just about the same thing, because the graph of cosine, because remember secant is the reciprocal of cosine, is going to be the same values as the graph of sine, just a little bit moved over to the side. So that's what the graph of secant is going to be. It's going to be the same as the graph of cosecant, just moved over a little bit to the side. The graph of secant will have a y-intercept of 1, because that's when cosine is equal to 1. And cosine has that 0 here, which means that secant's vertical asymptote will be happening at that point. So of course it also would be going up here too. And then the negative side is down here. And I'm just noticing now that my x-axes are not labeled, which is not very convenient. But this is just the regular parent function of cosine that I had graphed there. So we know that this is 2 pi, that's pi. And so the asymptotes were happening at pi over 2 and 3 pi over 2. And so that, what I have right now, is the basic graph for secant, except it looks a little bit weird like this because it's not really how it works. It really does keep going forever. So, of course, it will keep going forever and then repeating itself here, and here, and here, and so on. The asymptotes, domain range, it's all going to be very similar to cosecant. It's just everything's off by a little bit. Instead of having the asymptotes at pi and 0 and 2 pi and 3 pi and all of that, it's at pi over 2. And then every pi radians it switches off. So we learned how to write that last class also. We write it as pi over 2 plus pi n, which, by the way, are the same asymptotes as tangent, which means the domain is everything except those values. Since this graph looks the same as cosecant, just moved over a little bit to the side, moving over a little bit to the side won't impact the y values. So the range, which again I need to write down here so I don't run out of space, the range is the same, everything from negative infinity to negative 1, or from 1 to infinity. And the period is the same too, because even though it's shifted a little bit to the side, it's still taking just as long to reset itself. So those are the graphs of secant and cosecant.